In introductory engineering, we start with a clean assumption. We model electrical signals as completely deterministic functions of time. Under a deterministic model, a signal's exact voltage is completely specified. Knowing the equation reveals its state at any moment. On this cosine wave plot, lock onto amplitude A and period t0. Since it repeats flawlessly, calculating future values requires only basic algebra. But this mathematical perfection creates an engineering paradox. If a receiver can perfectly predict the future values of an incoming signal, that signal is carrying zero new information. An actual information-bearing transmission, like a human voice or a data stream, cannot be a perfect repeating sine wave. It must consist of randomly spaced bursts of energy of unpredictable duration. Furthermore, the physical environment of a communication channel introduces layers of chaos that standard deterministic calculus simply cannot map. To characterize these unpredictable signals and actually design working systems, we have to rely on a different mathematical discipline, probability theory. Building a functional communication network requires abandoning the illusion of perfect certainty and embracing the mathematics of randomness. When an antenna pulls in a transmission in a practical radio communication system, it isn't capturing a single isolated sine wave in a vacuum. The voltage it actually reads is a composite of three distinct, highly volatile components. The first component is the information-bearing signal itself. Its random amplitude and duration are exactly what convey data to the receiver. The second component is random interference. It takes the form of spurious electromagnetic waves generated by competing systems in the same environment. The third and most persistent component is receiver noise. This originates at the microscopic level inside the hardware itself, caused by the erratic, randomized thermal motion of electrons colliding within the conductors and devices. When you stack the unpredictable data, the external interference, and the internal thermal noise, the result completely distorts any clean, deterministic waveform. Because we cannot compute the exact future voltage of this distorted composite, we have to evaluate its statistical properties instead, such as the average spectral distribution of its power. The realities of hardware heat and channel interference require a shift in approach. Engineers must use calculus to characterize the signal's statistical behavior rather than its exact time domain coordinates. In probability theory, an experiment is any process whose outcome cannot be fully predicted because its operating conditions lack sufficient accuracy. Performing that experiment once is called a trial. The unalterable result of a single trial is the outcome. Every valid outcome must exist within an absolute mathematical boundary known as the sample space, denoted by S. Within this space, we plot the single, irreducible results of our trials. We call these individual points elementary events. When a specific subset of these outcomes shares common, observable characteristics, we classify that subset as an event. To analyze how often these subsets occur across multiple trials, engineers use the relative frequency approach. We take the number of times the event occurs, which we call n sub a, and divide it by the total number of trials performed, denoted as n. This ratio establishes rigid boundaries. If the event never occurs, the frequency is exactly 0. If it occurs every time, the frequency is exactly 1. The critical question is what happens to this volatile ratio when an experiment is run continuously, thousands or millions of times. As the number of trials, n, approaches infinity, the relative frequency ratio stops fluctuating and converges mathematically to a stable limit. This stabilized convergent limit is the formal probability of the event. Through this relative frequency limit, infinite and unpredictable physical trials harden into precise, reliable mathematical values. But we still face a structural barrier. You cannot plug a physical event, like a coin landing on heads or a static spike in a radio receiver, directly into an algebraic equation. The random variable is the mathematical bridge designed to solve this exact problem. Despite the name, a random variable is not an unknown number. It is a strict set of rules. It is a mapping function. This function maps every physical outcome in the sample space to a specific value along a real number line. Once mapped to numbers, we analyze them using the cumulative distribution function, or CDF, denoted as f sub x of x. The CDF measures the cumulative probability that the random variable will take a value less than or equal to a specified point, x. Because it accumulates probability, the CDF has strict properties. It is permanently bounded between 0 and 1, and it is a monotone, non-decreasing function. It can never drop. But for continuous valued random variables, evaluating a cumulative total isn't always enough. We often need to analyze momentary, localized states. To do that, we take the direct mathematical derivative of the CDF with respect to x. This yields the probability density function, or PDF. Because the parent CDF curve can never decrease, the resulting PDF curve will always remain non-negative, locked above the horizontal axis. By operating in reverse and integrating this density function over a specific range, engineers can recover the exact probability of an event occurring within those bounds. By mapping physical uncertainty to a continuous number line, the random variable re-enables the use of strict calculus for complex system design. The probability density function is anchored by one final critical geometric property. Looking at this chart, integrating the total area under the entire PDF curve equals exactly 1. It encapsulates 100% of the possible outcomes in the sample space. However, in a functioning communication network, engineers never evaluate just one random variable in a vacuum. They have to account for the incoming information-bearing signal and the persistent background thermal noise at the exact same time. This requires the joint distribution function. It allows us to calculate the probability that multiple interacting random variables will meet specified values simultaneously. By expanding into continuous joint distributions, we can precisely map the average spectral power distribution of a composite signal as it fights through a noisy channel. These probabilistic tools form the mathematical bedrock that makes advanced analog modulation and demodulation possible. Probability theory provides the mathematical architecture required to transmit and recover verifiable information within an inherently chaotic universe.